Alright, so we've downloaded that file. So now what we're going to do is set up the data to do the statistics example. So in this case, I'm going to do a few things. I'm going to import the data, and I'm going to set parse dates equal to the column date. This is a handy way to set that column as a datetime object right when we import it. I'm then going to do a group by date and get the mean. And I'm going to set that as the data frame. I'm then going to add, so it's going to give me basically the means of all those values for precipitation, elevation, latitude, and longitude. So latitude, longitude, and elevation won't change because they're the same for every column. If we looked at this data frame before we did this group by, we would see that. So I'm kind of doing a bunch of things in one cell here, just to quickly do it, but I'll explain what I'm doing. So then I'm adding column for month, which is going to get the month attribute, and year, which is going to get the year attribute, and then it's going to reset the index, so they're going to just number from 0 all the way to the end. So, and let me clear the output. So current all output clear. So that's fine. We didn't reset the kernel that time. I just cleared the output. So everything that we've already done is still stored in the computer. Okay, so we did all that, and now the resulting data frame has one row for each month. It's just numbered at the first of the month, and then we have the mean precipitation for that month. And then, so what we're going to do is just first of all have a look at the data so we can see the values. And then one thing I wanted to do was just make sure that the index is sequential. So if we plot by index instead of by date, we still get the same pattern. This just confirms that those numerical indexes are in the same order as the dates. And we'll see why I did that in a minute. So one thing we could do is, we've seen this one before, we can do the data frame dot describe, and this will give us all these summary statistics. We can get the mean of the precipitation, so we can say df.prcp, that's precipitation dot mean, and it'll give us the mean value for that whole for this whole column. We'll get the standard deviation of precipitation, which is quite high. It's higher than the mean. We can get quantiles. So in this case, we're going to get the 25th percentile, the 50th percentile, and the 75th percentile using this quantile function. And then I've just combined them as a tuple. We can get the minimum. And there's also this really handy function called Idx Min, which is the index of the minimum. So it will give us the index value corresponding to that minimum. So this would say, and we actually have 0 appears a lot. So this would be just, in this case, it is going to be, let's see if I do 10 here. You can see 0 here. I believe this appears more than once. So this is just the first instance of that value in this case. We can also, we have a corresponding max and IDX max method. We also have the ability to round the values. So if we wanted to round this value to the nearest whole number, we can use the round method. We'll see that in 1 second, how that could be useful. We saw this cumulative sum method. And then we have value counts. So value counts is super useful. In this case, what value counts does is it gives you the number of instances of a value. So we can see that we have 0.0 16 times. We have 16 months with no precipitation. If we don't have the round in there, we actually see there was 9 months with exactly 0 precipitation, and there's just a few. There's 7 more months that have less than 0.05 or less than 0.5, I guess. So it would be, yeah, just it's an example of how you can use value counts to kind of bin the data. This is also very handy with qualitative data. So, for example, we can do df dot like elevation. That's still numerical, but it's so we actually have a few different values in there, but that's just a really handy one. Okay, so that's like kind of the built-in stuff that Pandas provides. So now I want to cover regression analysis. This is a common thing you would do, and there's a few different ways to do it. So one is using Seaborn. So let's say we want to fit this monthly precipitation data to a line. So we can use the built-in Seaborn function regplot, and don't worry about we're going to see this warning a couple times. This has to do with some of the dependencies that Seaborn uses, and so it works. Just in the future, it might not work the same way. So what we're seeing here is all these monthly precipitation values, and we're trying to fit a line to it. So it doesn't really work that great. So let's say we wanted to change the order from 1, which would be a linear fit, to 2, which would be a parabolic fit. So we can simply pass this order argument, and we can see we get a much better fit. But this is really just kind of a convenience function. This is not, it's not very handy. Well, it's handy, but it's not as informative because it doesn't give you easy access to the coefficients and the p-values and that kind of thing. Gives you this like confidence interval, but it's hard to see where that's coming from. So if we really want to do a more rigorous fit, we can use NumPy. So NumPy has a function called polyfit, which is least squares polynomial fit. And in this first example, we're going to do a first order. So this is going to be a linear fit. So polyfit's going to give back the slope and the intercept of that line. And then, yeah, I can just, so this gives us the slope and the intercept. We can then plot the data and then plot the line on top of it, just using the basic matplotlib functions. And in this example, I'm not even going to create a subplot. I'm just going to do the quick and dirty plt.scatter, plt.plot to do a scatter plot and a line plot of the data, and then a line that's drawn from the data. So this is kind of just a quick way to see where that line is. And it's not a smooth line because I'm actually using all the months, and those kind of recycle a few times. So that's why it looks a little jagged. So if I wanted to sort by month and then replot, I could do df.sortValues by month in place equals true, and then replot that, and now I get a smooth line. But it still is not a great fit, so let's see what we can do with the second order polynomial. So here we're going to do polyfit, and this is going to give us, just like before, it's going to give us two values, but here we just had the slope and the intercept. These are the two coefficients, right? Well, with order equals 2, we're going to have 3 coefficients. So if we view this, we have the x squared coefficient, the x coefficient, and then the x0, or just the numerical component. So the way we can view this is, and this is a little more sophisticated than what we did before, where we just took the months and plotted them. We can just create an array from 1 to 12 that's finely spaced, so we can use this linspace function. We don't really care what the exact values are, but we just want there to be enough so that the curve looks smooth and not jagged. Then we can use this polyval function to take the coefficients that are in P, which is this 3 by 1 array, and then the values in this X array to get the Y array. So it's going to take each of those values and apply the x squared plus x plus constant using these p values. Not p values, the values that are stored in P. So now we're going to plot that curve, and now we can just do the same thing where we plot the x and the y data, and then we plot the curve using a line. So the nice thing about this is that we know what those coefficients are exactly, and we don't have to just have this graph that we can't get the information from. So we could do a third order fit if we wanted to, doing the same way, and it would look like this.
So this, sorry.
Yeah.
Does the PLT plot for like the look, does
Mm-hmm.
that come from the Seaborn conditions, or does that begin?
Yeah, good question. So the reason that you're seeing the Seaborn style here is because I did sns.set at the beginning, and that will inherit all the Seaborn defaults, even though I'm using matplotlib. So if I just want the matplotlib defaults instead, I just would not execute that command, and then I just have to restart the notebook to get those to. So if we do, I don't need to show you. You understand. So and again, I'm just doing this like quick and dirty to show you the results. But if I really wanted to make a nice figure, it would be better to do subplots and then to plot these to the axes, which we'll see in a minute. How, we've seen that before, but we'll do that today as well. Okay, so another fitting example that I want to go through quickly is fitting to a sinusoidal wave. So this is a way where you can have a certain kind of curve, and you can adjust the parameters of that function to get a better fit. And so the example we'll use is a sine wave, but you could do this with another kind of function. So briefly, to remind you what a sine wave is, it has a period, a frequency, which a period and frequency are inverses of each other, basically. It has a phase, an amplitude, and an offset. So we're going to set values for those here just for illustration purposes. We're then going to generate an x array and then a y array, which will be a function of those x values using the sine function that we just defined up here. So it's going to be the sine of x times the frequency plus the phase times the amplitude plus the offset. And then we're going to plot that. So we're going to make subplot. We're going to plot to the axes using the matplotlib plot function, and then we're going to set the x ticks and the x labels using a LaTeX style math equation for pi. Okay, so that's all going to go into this one command, and so we have a sine wave with all those parameters as defined. So what we want to do now is we're going to try to fit a sine wave to the precipitation data, because and now we're going to look at the dates sequentially, because we know, especially in San Diego, we have very periodic precipitation, right? It rains in the winter and it doesn't rain in the summer, and that's a reproducible thing. So we should be able to fit a cyclical pattern to that data. So what we're going to do is we're going to use the index, the numerical index, as our time axis. So first we want to do is make sure that the data are sequential. So we're going to sort by index, and so we have 0, 1, 2, 3, 4, and this is, and so on, and then we have the dates, one date per month. So first what we're going to do is plot the data as a scatter plot and add ticks to that every 12. So what we're looking at now is the precipitation on the y-axis and just the numerical index on the x-axis, and you can kind of see that every 12th month, which corresponds to December, each of these ticks corresponds to December. We do see kind of an uptick in the precipitation around December, January, or February. So what we're going to do is store those indexes and those values as separate arrays. So we're going to get the index and store that as t, and we're going to get the precipitation and store that as data. And then we're going to initialize the sine wave with some values. So we're going to start out guessing the period, the frequency, again those are tied, the phase, the amplitude, and the offset, and we're going to supply those as a list, and then we're going to create a function that will return the curve that we want to fit our data to. So this is going to be a function called mySine, which will be a function of x, the x value, frequency, amplitude, phase, and offset. And it's going to return, with those values, it will return a function containing all those inputs. So now what we want to do is we want to fit the data using those initial values, and then it will generate a curve that is optimized to the data. So it's going to take that sine function, it's going to take the x data or t, it's going to take the y data or data, and it's going to take a list of values to guess as this P0 input, and then it's going to give us a curve that fits. So if let's just take a look at this. So what we can do is take these as inputs to build a function, or to build the values of the fit curve. So we're going to take first we're going to use this sine function to take these x values, and then we're going to use this star operator to expand our guess, and then we're going to do the same thing with the fit data. So it's this first row of data that corresponds to those guessed or the optimized parameters, and we'll use the function on that as well. And finally, we can plot those results and see what we get. So we're going to plot the raw data. We're going to plot the fit after fitting, the function after fitting. We're going to plot the function based on our guesses, and then we're going to just put some tick marks. So what we can see is we have our data here in the blue dots, and then we have in green we have the original guess, and then in orange we have after fitting. So we can see that it adjusted some of those parameters. In fact, we can compare the frequency with, so let's have a look here. We can see that the frequency was almost perfect, so that period of 12 months was almost exactly right, but the phase, the amplitude, the phase, and the offset needed to be changed. So we can see, we can compare these four values, which were the fit values, to the original guess values. Questions on that? Okay, so we'll do one more regression example, and we'll do some outliers too. So just like you guys did for your assignment, I went and retrieved the moon and planet data for some of the largest moons. I had data for 23 moons. Maybe some of you had more that you could find data for. There's more than that in the solar system, but so I got data from those, saved them as Excel files, and so we're going to import those, the moon and the planet data, merge those two data frames together, and then add in columns for the moon and the planet volume, and then finally have a look at the data frame. Oh, so we need to download those, so let's go ahead and go back to our data, and we want moon. It's called moons and planets.xlsx. So we need to I think what we can do is you can control click and we can copy the link, and then we should be able to use that to do like a wget. So we're going to download moons.xlsx, and then planets is going to be the same path, but we just change the name of the file, and hopefully that will work. So go ahead and download those. You can also do it manually and drag them to the data folder. So we now run this again. Okay, now it works. So what we have now is a data frame with all of the moons and their planets and the various data about those objects. So first one we can do is a basic Pearson correlation. So this is just basically like a linear regression. First on the diameters and then on the volumes. So if we want to learn more about this, you can turn this into a code cell and run that cell to get the more information. I'll do that really quickly here. So it gives us some nice information about this. It takes an X and a Y array. So we're going to do that. Convert that back. So we're going to run this function. So this is a SciPy function. So scipy.stats.pearsonr, and we're going to do this on the planet diameter versus the moon diameter. So what this is going to, and we're going to store this output as the R, or the correlation statistic. That's the test statistic, and then the p-value. So we get a correlation of 0.39 with a p-value of 0.06. We can then do that same thing on the volumes, and we see that there's a better correlation between the volumes. So we get an R value of 0.52 and a p-value of 0.01. So that's Pearson. There's a related function called Spearman, which is a rank-based correlation. So this will just rank all the values and look at the correlation there. So here we get better correlations on the ranks than we do, well, with diameter we get a better correlation. With volume we actually get a worse correlation. So anyway, we can then plot those using the Seaborn function regplot. So we can see this is a different computation. It's going to give us basically the same result, but this is a way we can just quickly plot those. So we can see that there are some loose patterns here, but there's definitely some outliers. So let's dig into that a little bit more. In fact, we can see that for those of you that did the homework, you know that this one up here on the upper left in both these graphs is the moon, right? It's the Earth's moon, because it has a relatively large volume relative to the planet volume. So what if we actually consider that ratio? So we can add a column, moon-planet relative diameter and moon-planet relative volume, which will be the ratio of the diameters of the moon to its host planet using these columns. So we can just compute this as a quotient, and pandas will do it row by row. So it's really handy that way. It can figure out that when you divide one row by, or one column by another column, you're going to get a third column of the same dimension. That gives you those values. So here we're going to compute the relative volume and relative diameter. And now we're going to create some subplots, and we're going to look at the relative diameters and volumes. So what we can see is that now when we look at the relative moon, so this is the moon-planet relative diameter. So this is the diameter of the moon relative to the diameter of its host planet. That the moon up here is a big outlier. And if we look at volume, it's even a bigger outlier, because this is 0 here. So what can we do to get a better sense of these differences? So one thing we can do is we can plot the distributions using this Seaborn dist plot function. So here we're plotting, and I've labeled these like you might want to do for like a journal figure. So we have panel A here, which is relative diameter. This is a histogram and a kernel density plot, and also a rug plot, all combined in one. So we can see we have the moon over here. Its relative diameter is quite a bit bigger than the other moons. If we look at relative volume, the difference is huge. All the other moons are quite small relative to their host planets, except for the Earth's moon. So we actually have to look at a log scale. And this shows us that the moon is about, the moon to Earth ratio is about 100 times greater than any other moon-planet pair in the solar system. So the moon is really big relative to Earth, relative to other moons. So how would we test this mathematically? So this is why we imported this Outliers utils. So this is it's called Grubs Test for Outliers, and this is used to detect outliers in a univariate data set that are assumed to come from a normally distributed population. So we may be violating that assumption, but we'll charge ahead anyway. So so one thing we can do is we can print the outliers, and we see that we get a value here. So this is the value of the outliers. In this case, there's only one. If we want to know what that corresponds to, we can get that element from that list and compute, or just pull out that row, and we can indeed see that that's the moon. The moon is that row in that data that has a relative diameter of 0.27. So we want to remove outliers instead of using. So the Grubs max test outliers will give us the values that are outliers with an alpha of 0.05. So this is using a p-value cutoff of 0.05, or 1 out of 20. And then to get if you want to remove outliers from your data before going ahead, you can use grubs.test with the same parameters, using that single column of your data frame and an alpha here of 0.05. And this will give us all of the values minus minus the outlier. So if we want to do that with volume, it's the same thing. We can, here I'm going to set an alpha much lower, much stricter, just because it still comes out as significant. So that that volume ratio of the moon to the Earth is so much higher. So we can see that that's the row we're dealing with, and so then we can remove that outlier and we can proceed with the other data if we wanted to. Any questions?